Hey everybody, this video is designed to give you some insight into what a mechanism is and how we can determine the mechanism of a chemical reaction. So the mechanism is all the steps in a chemical reaction that happens between the reactants and the products. So if we have a reactants, and I am just going to make it, X, whatever the reactants are. And then we have products over here that are Y. Okay. Somehow those reactants have to go from X to Y, and they travel by a pathway. And that pathway is called the mechanism. Up until this point, we probably haven't talked about what happens between the reactants and the products. We've probably really just sat there and said, well, the reactants form products, and we don't think about what happens as they are trying to get to the products. And so that's what a mechanism is. Okay. Now, a mechanism is made up of steps. You can imagine that it's like following a recipe. How does the molecules get from reactants to products? Well, they go through step 1, step 2, step 3. And each of those steps are called elementary steps. Okay? And an elementary step is one single bond-breaking or bond-making event that happens during the reaction. And we can describe those steps by something called molecularity. Okay? Molecularity is this right here. Okay? It's a big word. It sounds kind of funny. Okay? So molecularity describes how many molecules, atoms, particles, whatever it is, are involved in the bond-breaking and bond-making steps. So a rocket surgery here, right? So unimolecular elementary steps have one molecule, bimolecular have two, termolecular have three, okay? On and on and on and on, but those are the three most common. And so now if we have a reaction like this, okay, like this one right here, example number 1. The idea is that we are saying that this is an elementary step. It's only one bond-breaking or bond-making step. And so what is the molecularity of that step? Okay, well, we have to be careful here because when we're talking about molecularity, I have a lot of students that'll say 1. Okay, yeah, I know what you mean, and that's fine, but let's try to get the terminology down that this is unimolecular. There's only one reactant here, and yeah, that one reactant goes to form 2 products, but in order for the reaction to take place, we only need one molecule. So it's unimolecular. And now here, when we look at reaction 2, this is a bimolecular. Okay, bimolecular elementary step. Okay, now I know, what if? Let's play the what if game here. What if we did have a coefficient in front of this? Okay, how does that change the molecularity? Well, the idea here on a chemical level is that we want to know, molecularity tells us how many molecules you need in order for the reaction to happen. So in order for this reaction to happen, this elementary step to happen, we need to have 2 O3 molecules and 1 O atom. Okay, so this is 2 plus 1. So in this case, the molecularity of this red equation with the coefficient of a 2 here, and I get it, it's not balanced, but if it were a 2 and it were balanced and everything worked out, that would be what we call a termolecular. So it's how many molecules, termolecular. Termolecular, right. Okay. Took me too long to write that. Okay, so that's that. The termolecular step means that we need 3 molecules in order for that reaction or that step to happen. If we only had one of these, that means that this reaction can't happen because we only have one. We need 2. Now the intermediates, okay, are the parts of the reactions that are made but then are used up again in the next step. Okay? They are part of the reaction. They're chemicals that are formed, but they're not products. So if we have a step, elementary step, where X reacts to form A, and then A reacts to form Y, okay, notice that X forms A, and then A reacts to form Y. That is an elementary, these two are elementary steps, but A cancels out. We don't see A as a reactant, it's not here, nor do we see A as a product in the overall reaction, but it is formed. And so an intermediate is that thing that is formed but then used up immediately afterwards. Okay, so that's what we mean it doesn't show in the overall reaction. Okay, so now we talk about the transition state. Well, the transition state is how all of this happens. Okay, how does X react to form A? Well, maybe what happens is X, maybe there's a bond in here between there that breaks, and so it goes here, and then eventually what happens is it forms A. Okay, now I'll explain this whole top of the hump thing here in a second, but transition states are not something that you can isolate. You can't stop a reaction in its transition state because it's moving toward the intermediate or moving toward the product. A transition state is only the moving through. This is really what it is on a chemical level, showing the bond breaking or bond making step or process. Okay, it's not until, so that transition state is not stable. It has a lot of energy, and chemistry wants to have a lot of energy. So let's talk about this hump here. Okay, what does that mean? Okay, so I have to skip ahead just really quickly. Okay, so what we can do is we can look at what we call a potential energy diagram or a reaction coordinate. Okay, that's kind of the funny thing here. Okay, we'll call it a reaction coordinate. Realize that this thing has a million names. Okay, but what we're doing is we're looking at how energy changes as the reaction progresses. Okay, so X and Y here are our reactants, and Z is the products. Okay, more on this later. The difference in energy between the reactants and the products, it's not delta G, it's delta H. That tells us that the reaction is, in this case, let's see, the reactants have more energy than the products, so it has to give off energy. So this tells us that this is an exothermic reaction. Okay. More on that when we talk about thermodynamics. But let's talk about this black hump here. Okay, I'll change my color to the black hump here. Okay, so here's what we're doing. We're actually tracking the energy of the molecule as it transitions from the reactants to the products. Okay, so that's what the power or the chemical translation of this graph is. This here is showing the transition state. Okay, transition state. It's going from here, it's going all the way up, it's high energy, and then eventually it'll fall back down and hit this reactant. Okay, now the height of this has a specific value that we call the activation energy. The activation energy is how much energy you need in order for the reaction to go forward, to go toward the products. Imagine that this were that we had a ball over here, okay, and we only gave it this much energy. Well, if we gave it that much energy, it's just going to go back and form reactants. It's not going to make it over the hump. The activation energy is how much energy we need to give the reaction in order for it to go from the reactants over the hump and down to the products. So when I say that the transition state is found at the top of the hump, so this is what the chemicals look like, and this is how much energy they have when they're going through the transition state. Okay. Now, before you get all bent out of shape, realize that transition states like this, what they look like, and that's beyond the scope of this class. We don't have to worry about what transition states look like, okay, or what's going on very specifically. The idea here that I want you to understand is that the transition state shows how the chemicals change the bond breaking and bond making step in order to become a product. Now, this in red here shows a different pathway. Notice what the difference is between the black and the red. Well, what we have done is we have added a catalyst. By adding a catalyst, what a catalyst does is, well, it does really one thing, okay? And we see the effect of that one thing. The one thing that it does is changes the pathway that a reaction takes, okay? It's a shortcut, okay? And so because it's a shortcut, what ends up happening is it takes less energy for the reaction to move forward. Now, there's some penalties for taking a shortcut. In this case, the penalty is that, notice here we have 1, 2, 3, 4 humps that are happening in between. Well, what this means is that this reaction, instead of happening in the black, it's happening in one step, one elementary step. In red, this is going through a transition state and then a low energy state. And then it's going up here through a transition state and into a low energy state. Through another transition state and down to a low energy state. Through a transition state and then down to the products. So the transition states are still at the top, but what do you think this low energy state is? Yeah, it's that's an intermediate. Okay. So the intermediates are all of these bottom humps that end up happening. The trough, okay? But that's what a catalyst does. It changes the pathway that a reaction can occur, that the reaction occurs on, so that we can lower the activation energy. So that way we only have to add, we will add less energy to get the reaction to go forward. Notice that the reactants are the same and the products are the same. It's just the path that it took to get there. In this case, now we have a mechanism that instead of having one step like in the black, the red shows that there's 1, 2, 3, 4 steps. We have X, whatever. X can form A plus Y reacts to form B, whatever, So, but the idea is that eventually all of these are going to add up to eventually just give us our product Z. And each one of these steps shows that there is an intermediate. And that's what this graph is showing. Okay, we'll call it a reaction coordinate, just to make sure that we have that. And those reaction coordinates are really kind of neat. Okay, but let's go back to where we were here, and let's talk about the guidelines for writing a mechanism. In order to write a mechanism, the slow step must reflect the rate law. Okay, now what do I mean by that? Okay, you're going to be given a mechanism that's going to have step 1, step 2, step 3, okay, whatever it is, okay, however many steps there are, however many humps there are on the graph, okay, and they will all be labeled fast, slow, fast, okay, or you'll see, one labeled RDS, rate determining step. However it's labeled, what you're saying is that the rate of the reaction is dependent on, in this case, step 2, because that is the slowest reaction. So in this case, the rate law has to reflect whatever the stoichiometry is of this elementary step. And so it's going to be to some value n, and n in this case now can be the coefficients. Okay, so that's how coefficients play a role in determining what the rate law is or what the mechanism is. Okay, up until this point, we've never once used the coefficients to determine kind of what the rate law was. We've always had to use method of initial rates, or we had to do it by some other means. Now we can use the mechanism, to determine the rate law and determine if it's first order, second order, whatever. Okay, and like I emphasized, what we just went over, the number of humps in a potential in a reaction coordinate shows how many steps there are. So if there's 4 humps, there has to be 4 steps. And in the last one, and I think that this seems a little obvious, but I will still say it, is that all of those elementary steps have to add up to give the total reaction. And that's something that is a kind of a simple check, but it's something that people forget to do. Okay, so as long as it fits these 3 criteria, the mechanism is valid. Okay, I get it. There's a lot of different things going on here. It seems kind of, I don't know, ridiculous. Maybe not ridiculous, but seems kind of not mathematical. It seems kind of abstract. And yeah, it is. Trust me, it gets less abstract the more you know. Finally, something that's kind of backwards a little bit, right? The more you know about mechanism, the less it's abstract. But for now, the easiest thing to do is just keep in mind these three points when you have a mechanism in front of you. Okay, so here's an example. Okay, you're given a reaction. Okay, and it says that this is a possible mechanism. Okay, now let's address these questions. It says, what is the molecularity of each step? Well, let's see, what's the molecularity of this step here? Step 1, the molecularity is, again, fight the urge to say 2. It's bimolecular. Okay, the molecularity here is bimolecular, and this one is bimolecular. All 3 are bimolecular. Okay, what's the next question? What is the rate equation for the 3rd step? So let's assume that this is the slow step. Okay, well, the rate equation, because it's an elementary step, okay, because it's a mechanism is made up of elementary steps. What we can do is we can write the rate equation as R equals N2O times H2, and both of these are raised to the 1st power. I always put the 1st power there because I just want everybody to know that I know that it's the 1st power. I just didn't leave it blank. Okay. Oops, I went the wrong way. Okay. And it says identify the intermediates in the reaction. Okay. The intermediates in the reaction are those things that are not reactants and not products. Okay. So that's kind of the easiest way that I know how to say it. So NO, that's a reactant. N2O2, that is an intermediate. Notice that's not a reactant or a product. Okay. Now, if it's an intermediate, it should be used up, and lo and behold, here in the second step, notice that it's used up. So it's still an intermediate. Now, H2 gas, that's a reactant. N2O, that's an intermediate because this guy is not a reactant or a product, and it has to be used up, and lo and behold, it's used up. And then as I look, let's see, H2 is still not an intermediate because it's a reactant. N2 is a product. H2O is a product. Okay? And so now, last but not least, it says, show that the sum of these elementary steps give the equation for the overall reaction. Okay? So to summarize these, it makes it really easy, or easier, if we keep our arrows kind of all lined up. Okay? I'm particular about this. Not that you have to be particular about it, but I am. And so what I'm going to do is I'm going to continue my arrow down here. And I am going to write all the reactants on one side, 2NO. And I'm going to leave off the states because it takes up a lot of room. Let's see, N2O2 plus H2. So I'm taking these guys and writing them here, plus N2O plus another H2, reacts to form N2O2 plus N2O plus H2O plus N2 plus H2O. Okay, so what this does is this shows us what is on the reactant side and what's on the product side. Now, let's be real for a second. This is not the final answer because this does not equal that. Okay? But it can, because watch what happens. What I'm going to do is I'm going to reduce and combine like terms. So let's see here. We have N2O2 and N2O2 on each side, so they're going to cancel, intermediates. We have N2O and N2O on each side, so they're going to cancel. Now we're going to combine like terms. Notice we have 2H2O, and on this side we have 2H2. So we have 2NO plus 2H2 reacts to form N2 plus 2H2O. So is this reaction, does it add up to the overall reaction? Absolutely. After we go and manipulate the equation by combining like terms and canceling out the intermediates. So this fits the mold of being a possible mechanism. Okay? This fits the mold of being a possible mechanism. So we have answered that question. Now, just really quickly, let me go back here. What would a potential reaction coordinate look like for this guy? Okay. Well, let's just really quickly talk about it. Okay. The reaction coordinate for this guy, and I'm going to write it really small down here. Okay, we're going to put energy here. We're going to put coordinate here. I know it's such a weird x-axis label. Okay. And so now, how many humps do we have? We're going to have 3 humps. So we're going to go up, and we're going to go 1, 2, 3, and then down to the products. Now, we don't know what the activation energy is. We just know that it has to be higher than the energy of the reactants and products. And we don't know if it's endo or exothermic. So we just kind of make some guesses. What we do know is that there has to be 3 humps. And that's about all we know. Okay, so this is a possible reaction coordinate for that mechanism. Okay, so last question. It says oxygen does all of this. It says the rate equation. Okay, so it says, can this rate law or rate equation be for this reaction? Okay, or I'm sorry, be the bimolecular. Can it be the elementary step? Can this be the only, I'm sorry, can this mechanism happen in only one step? Um, that's what it's asking. And the answer is resoundingly no. Because if we have a rate law, the rate law has to reflect the stoichiometry, the coefficients, stoichiometry of the elementary step. And so that means that the elementary step has to be NO2, and there has to be a 2 there, and that has to react to form something. Well, that has to be the slow step, the RDS. That is not what this is, so therefore this cannot be, this reaction cannot happen in one bimolecular step. It has to happen in 2 steps or 3 steps or 4 steps, and one of the steps has to look like this, where we're forming something. Okay, so that goes over what reaction mechanism is, and feel free to go back through and look at what this has to offer, and have a great day.